This is the continuous memory allocation, memory regions session. So mostly general topic.
Okay, let's see here. Okay, so the continuous memory support, there's several use cases for it. One of them is where you have some device that uses Codex-like camera or something like that.
But we just want to take notes as we need. What's all this in there? Take notes. Since disturbance in the force in that area, one of you two. Oh, come on.
I can't run Kobe on my laptop.
I've never going to do it by until life.
You can use my laptop.
That's in French.
Yeah, I can use Google Translate. I know how that works.
The name of the session is, I cannot say it. What is it? Is it OSA or hardware? What is it? Something OSA.
Yeah, that's it over here.
Control L and?
No, I just go over.
If you go to the, look at the URL, you'll see.
Yeah, if I turn the laptop around so that my brain will work right, it'll be better. Okay, so this case.
Is it, so what is it?
But how can I too can pass my laptop?
Performance.
Performance and
document, which contain performance and kernel memory regions under the performance directory.
Thank you. All right.
You have to have your actions at the end, the button actions or things going to be something.
All right. So, yeah, this is painful. All right, so there's a couple major use cases of these things. One of them, again, is something like a camera, where you have a codec that doesn't have an I/O view, but it needs contiguous memory. In the case of something like a camera, it needs that memory only when you're actually actively taking a picture. All right. If once you take the picture, the memory is essentially used. Yet that's the way things typically work for SoCs these days, for devices these days. You reserve the memory boot time, and that memory is tied up whether you're taking a picture or not, and that works, but it's kind of wasteful. So one way of getting around that is to make use of some of the memory defragmentation or the memory coalescing patches, some of the work that's been going on. Get that fixed up for this case. So it's called memory regions. And the idea is to define multiple memory regions. For this particular use case, you would define a region that covered the requisite physical memory. And you would label that region as being unavailable for kernel allocations, for example. And what would happen then is there might be memory allocated there, but it would always be memory that could be moved, that the kernel would move if it needed to. All right? So because of that, what would happen is that when it came time to take a picture, you could go through and move the memory out, evacuate the region, which could happen quite quickly. It's much faster than the reflexes, so the guy pushing the trigger is not going to notice. Okay? You can push the trigger down and you can get the memory cleared out before he has a chance to actually move it all the way down. And then use that memory to take a picture. Once the picture taking is complete, then allow allocations in there so that other tasks, for example, using the camera UI to change settings, reviewing old pictures, can make use of that memory. So that's one use case. You define a memory region to cover some contiguous physical memory. You prohibit non-movable allocations in that chunk of memory. And then when you need to use it, you clear it out and take a picture. The other major use case, the other different kind of use case, involves power conservation, power savings. And the idea is that if you have a embedded system that rarely needs all its memory, and if the power domains on that system break the memory up into banks that are split out so that the addresses line up nicely, then you would normally have the upper banks of memory, for example, powered off. If you came to a space where you needed them, where the application, where the user was running some application, doing some operation required for memory, you would power them up, get them set up, and allow them to be used. There we go. And then, oh, okay. Sorry. Oh, okay. We got those. Okay, thank you. Thank you very much. So then, what can happen then is when it's being used, you can power them up, they consume more power. But again, you restrict them so that only certain classes of applications can occur. I mentioned before that they might be just non-movable applications. But in this case, it may be the memory is being consumed because some particular process, some particular program or application is being run by the user. In which case, you might restrict the upper memory regions to only have allocations for that process, non-movable applications for that process or group of processes. And that would mean that when they got done with that, when the process died, the memory would just go back to the system anyway, which would allow you to, once the process was killed and its memory cleaned up, would allow you to power that chunk of memory off. This is hardware specific. You have to have hardware to use it. The second use case. The first use case is mostly media codecs, cameras and things like that. The second use case is for hardware where you have multiple memory domains. There are some of those being planned, and where you have applications that have high peak and mean memory usage. In other words, they can at times use a large amount of memory, but most of the time they fit into a much smaller memory footprint. There's been some vendors are enthusiastic about that, other ones don't see the need for it. But that's given that it depends on the SoC, that's not surprising. So that's kind of an overview of what this contiguous memory allocation is about. Basically, the big point of it for the first case is to allow memory to be reserved for media codecs when they need it, but to be used for other purposes during the times when you aren't actually using that codec. And the second one, if you have situations where parts of memory can be totally powered down, or even refresh turned off on those parts, doesn't give you as much power savings, but it's another approach to it, that you can use that memory when it's needed, but leave it powered off when it isn't. Thus, I think somebody was estimating something like a 10 or 15% battery lifetime increase in every particular application if they did that. So any questions on the overall purpose of this topic?
Your second use case.
Second use case.
So you're powering off some memory. Is that via memory hot plug or is this a separate?
It's related to memory hot plug. So there's a memory hot plug type of a thing that's used in some servers where they actually pull the chips out, put them in. And also, it's one way of dealing with virtualization, where you may have different machines that you grow or shrink the memory over time. And we're using, and the memory regions is a mechanism that has been developed in the server space where that we would be modifying that. We want common code, right? We don't want to just duplicate it and do things.
I don't know whether the memory hot plug is functional or not.
It will need some help, and there are some, and IBM has some people outside of Monaro that are working that in the server space. And so this is helpful to them because they're doing something farther out, and this gives them a short-term use case, which means they get the code changes in the kernel quickly, so that they don't have to kill themselves at the last minute. And otherwise, the maintainers say, well, we don't see any use for that. Why are you doing that? Well, we will, but and this allows them to have a near-term target so they get the core changes upstream and just do the architecture-specific stuff later when it's there. So yes, it's there is some work required, and yes, we're getting some resource outside of our to do so.
So I've got one more use case that's kind of a combination of yours. You can, for performance reasons, you can want to have various bus masters on different banks of VRAM. Those will give you higher performance. So you may want to allocate buffers for video buffers in one bank, graphics buffers in another bank.
So the idea is that you may have different hardware associated with different banks, and that bank might be dedicated to that hardware. And if you aren't using that hardware, you power the bank off as well as hardware being powered off. Is that fair?
Or you just to allow the drivers to specify which banks they allocate from.
Okay, and so the reason that's interesting, I mean, if the hardware was making full use of all the bank, it wouldn't be interesting. We would just associate the memory with the bank, and the current kernel would work just fine. The thing would make it, the reason you would need this is if the hardware used, say, a half a bank, and then the other half was available when that hardware was there for other allocations as long as they didn't connect the bank from being powered off. Is that right? Is that the idea? Okay, cool.
What if our system that runs out of memory? That's still possible.
Yeah, well, if you have all of your memory in use, and you run out of memory, you run out of memory, and that would be the same as today.
And launch the camera application, so it's not able to.
Okay, so that's why you have the restrictions. So let me talk about a couple different ways of doing that. For example, it might be, today what you do is you reserve that memory and stay reserved forever. You just wouldn't ever be able to use it. So you run out of memory soon. Right? Because, let's say you
Application one, when they fail to add memory, the memory is reserved.
Even
Right.
anything else on the system.
Right.
At this point.
So if you run out of memory soon. So let's suppose that you had the reason you need more memory is there was some application that would run occasionally to do things to the pictures that are already taken. I'm right, you view them, maybe adjust the price of the contrast on them, or something like that. You normally do on post C. I'm just taking that as an example. If you've got a better example, tell me what you use that instead.
Yeah, Restwood.
Restwood?
You can page it out.
Yeah. So if you only allow, so let's say you have that memory that was normally for the camera. Now, if you're viewing your pictures and playing with them, you're not taking a picture. So if we did it the old way, we could run out of memory because we've uselessly reserved this. It's not doing anything right now. You're not taking a picture, but we can't use it when we run out of memory. Whereas if we say, okay, in this chunk of memory, in this reserved piece of memory, we're only going to allow memory allocations where the memory can be moved. Okay, then we won't run out of memory soon. Okay, and if we make it so it can be moved, or better yet, if that memory can only be used by a process only running when we're not taking a picture. Okay, some element of the UI, for example, the part where your camera is reviewing pictures, or doing something, if that runs as a separate process, or if it allocates the memory and then frees it, separates it out, either way. Then what would happen is it could allocate that memory, continue going, or you could have a smaller memory in your camera, whichever makes sense. That's best enough.
So how do you declare those kind of restrictions?
How do I declare those kind of restrictions? Memory regions has a facility where you have it's something you do in the kernel, and there could be a user space interface to it. Okay, but what you do is it's a tabular thing where you indicate the region where it begins and ends, what its identifier is, and what sorts of things you've done with it. So possibly restricting it to movable allocations, restricting it to allocations for a given user ID, if that makes sense. It makes sense on the server side, might not make it embedded. How many users do you have on camera after all? Or a given process.
Okay. Probably you could by default allocate only non-private read-only pages that can be drafted.
Yes, that'd be an excellent example. Have it so that it only does kernel program text, for example.
Yeah, you don't have
Not
to
shared
copy any of
language.
it.
Yeah, and if you throw it away and pull it back when you need it. Yes. Or you could have buffer cache pages.
Yeah.
Page cache pages being the only thing there. So So there's a number of, depending on your application or something, there are a number of different strategies you could use to allow certain types of memory to go in this region. So you either easily drop them, move them to other memory. In other words, you could go through memory and drop other things and then move these down to take their place. Or just putting things there you know won't be in use needed at all. It will just disappear because the process exited. Or because the process struck its memory. Right? It allocated memory to store a bunch of photo images because you're scanning the photos, and then you say, I want to take a picture, that it throws that memory away and either has the memory available in that region to use or has a place to move the stuff out of that region to make that physical contiguous region available to take a picture.
Have you got an idea of the latency for reserving or making available this memory relation?
So so there's a couple pieces to that. So the question is, do we have an estimated latency for getting out of it? And of course, it depends on the size of the memory. My impression is that for these codecs, it's a few megabytes. Maybe I'm confused, but
Maybe not for codecs that is there. Or maybe it's become more and more larger.
yeah. So maybe so what do you want? 20 megabytes?
Yes, maybe.
Okay. 50 megabytes? 100 megabytes? What? Oh, well, give me a number. What number?
Yeah, 20.
20. Okay, we'll use 20 megabytes. I'm happy with that. So 20 megabytes, if you've, now, so the latency will depend on the situation you're using. Let's say we use Nico's approach, where we just only put memory there that we just drop. Okay? In that case, we're doing a few memory writes and a few lock acquisitions. And I believe we can do that in certainly under 200 microseconds. Or in the case where it's just real-time, where we just say, you're not here anymore, go away. Maybe it's much of that than a millisecond. Okay?
It's really quick.
It's really quick. If you actually had to move the memory, okay, so let's say that you were doing the situation where you have the memory up there only for movable allocations, all right? And you are using the extra memory for something that isn't there when you're taking a picture. So you may, for example, maybe some GUI is part of the application where you're displaying pictures or something like that, and that gets terminated. Okay, because it's terminated, you know you have enough memory, it just may not be in the right place. Okay, so you may have to go and move that upper chunk, memory to memory. And so you got 20 megabytes that has to be moved somewhere. Your memory bandwidth has got to be at least, I don't know, 500 megabytes per second, right? Okay, and at that point, you're down in a few milliseconds range. A longer case would be as if you had to write flash. Okay, with stuff that you knew you'd get rid of, but it might be dirty buffers, for example. You might need to put page cache buffers there, or your process would go and do MAPs to flash and write to them. And so then you might have to turn around and write a flash. In that case, your latency is longer. I don't actually recommend that for a camera because it might take a while. Now that could be okay if there was a bunch of things the user had to do to get from this mode where he's in this GUI and he's doing something, an example, like that before taking a picture.
Yeah, but then you're back to a situation where it's basically a swap file on Flash.
Yes, and that's right. So my advice to you would be to make sure you're in one of the first two situations that you're going to use this. Unless you got a really fast flash device, which takes still a while.
Is there any, is there any kind of convoluted case where you may want different memory attributes, a different kind of mapping, say camera buffers or something, than a normal memory? So then you can't use that, so if you use it for other data, it's not cacheable.
In that case, I would hesitate at this point to try to use it as anything but the intended use. So what you're saying is you might have some memory that.
Oh, I don't know, it's kind of an open question, and then people would do something like that. You might say, I don't want to pollute the cache with this camera data or something, it's an uncached memory.
Oh, okay, well, you can, I don't know about which arms can do this or what they do. I think you can mark, like, if you remember, it's non-cacheable, can't go without confused. I've got too many architectures in my head, I can't keep track of which one's which anymore. But that's not where, nobody's asked for that yet. And if somebody has a specific situation, SOC that needs that, let me know. But I haven't heard of one, so I'm not doing it.
Yeah, I do too. I don't know anything.
DMAC in the memory or something.
You don't remember? Just flush it. Hardware codec.
Is there a strategy to put all the non-movable memory in one region as well?
Oh, in the simple case, you have two regions.
Yeah.
You have one region for the memory that's to be used for the camera, and you have the other regions for everything else. And the other region for everything else will say whatever it is, put it
Okay,
out
so
there.
there's no, I mean,
Oh, you want a region that only has
yeah, I mean,
unmovable stuff?
well, not to read, I mean, at least to have it together, so it's not fragmented. I mean, to have non-movable memory, not fragmented over my memory. So if I want to run and then put all the memory and compact it, it's not possible if the non-movable memories are spread out.
So, okay, so let me try to state what I understood from what you said, and then you tell me whether I got it. How's that? So the idea is that you initially you have one memory region that's a certain size and that's what you're coding. But you have other occasions where you need more memory. But you don't know how much initially and you don't know what it is. So what you want to do is you want to squish your non-movable regions down to the smallest possible thing. So you have the largest chance of getting the largest and biggest buffer possible.
Yeah, so in this case, maybe I didn't have a real use case in mind, but if I have low fragmentation on my non-movable memory, I have a bigger chance to maybe more flexible, have a big large chunk of continuous memory, or even to turn off more banks if I move around the memories.
I'm trying to think of a use case for it. I'm having a little trouble with it. My initial reaction, the first thing that came to mind when you said that was that if you need memory quickly, you should make sure the region just doesn't allow. You should have a region of the perfect size that just doesn't allow the perfect mappings, the non-movable mappings. And that way you guarantee you get rid of it.
Yeah.
The sort of thing I can half imagine, I suppose, on my camera, which is a cheapo camera, so maybe just a cheapo camera, right? I don't know. But if I take a picture, it takes a while for it to get its act together. I mean, it takes a while before I see anything, before I really go with it. Like, that part of a second.
But I think I'm more into use case number 2 when turning off.
Turn the power off. Oh, okay. Okay. In that case, the way I would suggest doing it would be to have a separate region for each bank that could be powered off separately. Okay. And then restrict the non-moving mappings to the minimum number you get away with. And you probably do that as a proving exercise, going through it and seeing how much there was. Give yourself a little safety factor, right? So if you could split it into, I don't know, 16 regions for your DRAM, and you found that your worst case test use 2 regions, allow 4 regions to have non-moving mappings.
Probably you can mark all of them in movable locations, and when you don't get any space in the non-movable regions, you just pick one movable one and translate it to the non-movable.
Yeah, that might make a lot of sense. We need to check and see if that's going to make sense in the current implementation, but from a use case viewpoint, that'd be great. So
Because it will scale automatically with the usage of the non-movable usage.
So the idea is to start off with a very minimal amount. You have to have at least one mark to allow non-movable allocation.
Yeah.
So the kernel, of course.
Yeah, exactly.
And then as you get more non-movable data, just mark more of them moving up there as being, this can have non-movable
Exactly.
data.
Up to a certain minimal threshold.
Yeah. And then you can scream if it's more than you expected or something, I suppose. I don't know if that makes any sense. It does make sense.
You need to then do some weird kind of packing stuff to get freed up, so you don't end up with holes.
Well, I suppose one thing you could do is if you start approaching where you're filling up a region that you're going to do a non-movable allocate somewhere, you could try to evacuate yourself. It wasn't movable out of a non-movable thing.
Is the idea here to have one region represents one need? So if you have one camera that needs one buffer, you should have one region for it. Because what we have in our platform is that we allocate a large chunk of contiguous memory, and there we have all sorts of media buffers. We have camera, we have media streams, audio streams, all that kind of stuff. And then there's some page allocation algorithms to sort of reserve buffers in this area. So we would more or less have to reserve different regions for each one of them.
That depends how you want to set it up.
Yeah.
One, in terms of there's a bunch of things, our different address range restrictions for different devices and a bunch of other stuff.
Luckily, we don't have that.
Okay,
But-
that's good.
But it has to be
the hardware
continuous.
guys trained. That's good. Or at least trained for right now. Okay, so what I would, my naive immediate answer, which I'm saying is a starting point. I mean, you get into the details and who knows what happens, but would be to say, okay, what's the sum of the size of the buffers?
Yeah.
And have one region that has that much and say, we only have movable applications.
Yeah. As long as, but then it's
It's really simpler if we could have an API for each driver to just say, I will need this amount of memory, just reserve it for me. And when I ask for it, give it. So each driver would be responsible for its own memory needs.
And then when they do time, they register those memory needs.
Exactly.
And then that sets up the memory needs. That's
so
actually.
you can concatenate the needs of all the drivers. You say that okay, this chapter memory is
makes a lot of
needed.
sense.
But then I wonder if that will end up in practice with current implementations in, say, one of all of these drivers, once it's chunk of memory, then all of it gets evicted because it's just one big region.
Well, you gotta be careful, because if they don't want contiguous, you have to start from one end, because you have to pack it, right? If you just start allocating it, oh, we got lucky this time, then you may have prevented the other guys from getting by,
Exactly.
in a strange place.
Yeah, that's why we have to add them up, so that we
Yeah.
at least we guard against that. But I
So,
mean, if one of them needs a buffer, we have to evict everything that's in the other.
Well, so what I think it means is that we need, this is something I hadn't considered, that we need an API that says, give me throw out my allocation and have it be, instead of just giving the whole region, evict this much.
Yeah,
evict down
exactly.
Here.
Yeah, that's what I'm after.
Okay. Sounds reasonable. I want to talk to people actually at work and see if it sounds reasonable. How's that?
This is close to exactly what we have implemented, but by just restarting off large.
Okay. So the idea is then that might also allow the drivers to work more similarly, because I mean the drivers already say they already do the reservation, and so this would be just changing that API to say make sure that this memory is available for them. Okay. Cool. So I guess going back to what was raised earlier about running out of memory, that was you correct. One thing that could happen is when it came time to do if the system wasn't designed well, when it came time to do the picture, you could find out that there were a bunch of movable allocations and evicting all caused problems. But that situation is exactly the one where you're going to run out of memory before you got there. That line of reasoning is why I thought it was okay, but that's something to keep in mind. It's sometimes, even though you would have run out of memory anyway, it's still upsetting for whatever reason.
But with any other scheme, you would have run out of memory anyway.
Exactly. Okay, so at some point here we should start thinking about actions. I've got the action to take back the new things we discussed to people in IBM for implementing it. It sounds like one of them is a boot time reservation, so you just add up the driver's reservation, say this is how much you're reserving, as opposed to having a hard table somewhere that just knows what it is.
Just one note, this presumes that the drivers are compiled into the kernel.
It does. Aren't they usually in this domain?
So, no, I just wanted to say that this may not be doable in all cases.
So you're thinking of a
You
case
may want
where-
to load the camera driver during runtime.
Or maybe you can have a certain registration that you know on your SOC, if you're using the camera, it might need that amount of memory to reserve that, even if the driver is not loaded.
Maybe more specific, like.
Yeah, things like that, but I don't think that you might be in the need for a compute memory which is so large that it would prevent the system from running even if the driver is not used. Because it is reserved, but it can be used for the other purposes until the driver come and claim.
Right.
And it sounds possible that you could dynamically resize this region anyway. You find out something that's on the end and move that, or providing it's
Well,
movable.
you can fail. I mean, in other words, you have the region already there, you want to make it bigger, all right? Well, it could be there's non-movable just right at the edge of it on the other side, in which case, so
So is there any way we can delay that from happening for as long as possible, or?
That's the
well,
question.
that comes back to Nico's idea, which is to split up the, so you got the the region you're preserving, and then split the other one up into chunks, and then allow the non-movable to go up as needed.
Cluster your allocation.
Just wondering about the second motion, the once motion, down action.
Yes. Okay, so, so I started up on that, and
Yeah,
then after.
just want to make sure
You guys are good.
that I have time because
Anyway, what I need to do is take the additional use case and APIs back to the people working on it and validate those and figure out what else can be done, not all can be done. We need to, there are some people that have mentioned an interest in it, and so we need to get them identified. I need someone to sign up for doing testing in this site. So we can show the code and get some, at least look at it or working with it or something.
Well, since we have people here who implemented some other solution in the meantime, maybe they're good candidates for that.
Yeah, we can run our, like, how we reserve piece of memory, static piece of memory, then we have a driver using that memory pool. But instead, we could just use the same driver, but using the dynamical and continuous memory.
The main thing you have to do is add, if you don't already have it, add an API. Oh, you've got one where you just have it set up and you say, give it back, sort of thing.
It's like we reserve a large pool.
Yeah.
This is, just taken away from the, and then the different media use cases will go in their reserve pages.
Okay, so you already have a reservation step saying, give it to me now, okay, I'm done with it.
Yeah, so
Give
it
to me now,
should be
I'm done with
easy
it.
to move that into using.
Okay, so what I need to do, Venus, I know who you are, and I'm not,
This is bad.
What?
Half holiness.
Oh, okay, great, okay. So what I need to do is get you guys connected with them so that we can, okay. So I'll take the action to get Venus and Pablo hooked up so we can make sure that we're getting that set up.
We have someone from our house.
And I've already got you guys hooked up, right, or am I confused? And there's another group that I'm working on where we have our getting it set up.
Is there somewhat related to what one of the Samsung guy was working on?
Yes, and Tree is around. I don't see it there. I think it was there Monday, Tuesday, or maybe it was make it all hammer. And so they sent some slides, which I forwarded on to the group. They took a look at them, and the slides are at a high API level, and they're kind of working down here at the low level at the moment. But they felt that the APIs described in there were consistent with what they're doing. The real cool thing is that that Tree is there are a bunch of guys in Bangalore. The guys actually doing that IBM work in Bangalore. It seems like Bangalore is the place for this stuff to happen.
But if a bunch of people are converging on the same needs and the same implementation,
That's good. Oh, yeah.
you only need someone to coordinate everyone's action.
I think that's
I guess that's you.
yeah. Yeah. So that's why I'm taking action to get people together.
That's really cool.
Hopefully we can get some. Hopefully it allows us to turn some memory down and make it work that way.
What is the current status? Is it like something proof concept already?
There's some early proof of concept stuff that doesn't quite do everything. But what I'll be doing, one of the things I'll be doing is reporting out occasionally where things are. The reason this is workable is because there's been a bunch of work over many years actually in the kernel space to get some of this stuff in place. So it's building on a lot of what's happening now.
So back to the second usage, like memory can be cut off, some part of the memory can be cut off. So the exact operation can be SOC specific. So other than need something. kind of
Yes, and so one of the things, if we care about that use case, what we need is people associated with the SOCs to try it out and make sure we get an API for it. What would have to happen?
But you don't need a special API for that. You just need to, okay, I want to power off this memory, so you use the generic API to say, give this memory to me, and then it goes down. So, yeah, but you just grab it from this generic API. When it's your own, then you can power it up.
True.
You would like to know if there is any application.
Well, when it's located to you, you know that there's nothing.
Right.
Oh, yeah, it is, yeah.
Okay, so the reason I was hesitating is that, and that's the way of doing it. I'm wondering if there's some common code that come out of that. Obviously, the little piece that actually turns the memory off is SOC thing.
Yeah.
But is there something we're doing, some of the deciding when to get rid of it and things like that?
Yeah, that might be common code.
Right. And I mean, the initial thing would be the application just decides, sign to shell a bunch of memory, and I know I'm not doing anything. And then, as a driver or something, do that. But if we get more common code, we get that. But you're absolutely right. That strategy implementation makes a lot of sense. Just use the API to clear the memory out, and it's yours.
What you may want to do is, okay, there is not that many regions, so finding out the empty regions will take too long time. Would you have each region see if you manage to fail or not?
Well, it depends on your use case. The use case I was considering was where the device was doing something with people out of memory, so power memory out. And then when that got done with that, it says, okay, I know I'm not using very memory, therefore I should be able to give back 100 megabytes, whatever.
Actually, it can be dynamic because if you have all those movable regions which are not in use, you can power them down and just power them up when they're required.
Yeah, so you could say, all right, I'm using only 60% of memory, so I should be able to. So I got 40% unused, so I should be able to power off 25% and not make trouble for a while, for example.
Yeah, and you're just making a gap of free memory available for allocation, and when that gap is getting too small, you just power up some memory.
Right, but either way, the thing that we would need are some people with SOCs to try that use case out.
So we have to have a clear definition class of this SOC?
Well, I think that the main difficulty I see here, complexity, is in the generic code to provide that API. Once that's in place, people will start using it.
Okay, so should we do our first these actions this cycle or something for second cycle? Do we just do the generic code this cycle? Or?
I think doing the generic code this cycle makes a lot of sense. If it gets done faster than we expect, we can adjust, right?
Okay, what kind of test plan we have for generic code?
The test plan is to go through and torture the thing. In other words, run something like kernel builds. Okay, set up the region, run something like kernel builds, kill the kernel builds, verify you can actually allocate the region, and do that kind of thing. And you can do it with various sizes of things as well. One of the deliverables would be to get a better test plan. Actually, that's probably a good action is to identify get the test plan out.
Tom should have some notes.
Okay. Okay, that's even there. Easy tab. Why don't you look at that?
Just go, yeah.
Oh, all right, there we go. Okay, yes, we do have to get a better test plan. And what I would do is get the test plan together and circulate it. Okay. So I think we've got four on this.
Okay. Do we need to discuss something further on our revisions? So we happy? Jumping through it? I certainly see a Thursday evening as going on first. Okay, well, I'll just do another session then if you're happy with the actions. Then you want to read the actions out to make sure we're happy with them?
Let me do that. Okay, so here we are, actions. Okay, okay, the action is, one action is the core work, which is getting API for the driver. The additional things, I need to go check and see if they have API for the driver, boot time will say I need this much memory. And then create the region at boot time for whatever dynamics the driver sees. And then there's the API that's already in plan for doing the allocation and looking at it for a certain amount as opposed to a big whole thing.
I think you should mention kernel modules in the first point, because that
Okay, that's a good point. I'm not sure who's got it. Okay, very good. So kernel modules that are loaded late at runtime. I thought the resolution was to have a sit at the boot time corresponding to if you do the reloading to
yeah.
yeah. Another approach is the thing someone we got together to suggest, which was, well, let me go through the rest of the action. Okay, yeah, we got the boot time allocation hard table there. Assumes driver applied to the kernel, might be board specific, and a board file device tree might deal with it. Linus and yeah. Oh, okay, gotcha. Are interested in testing, and we got Drew for Samsung, custom format. There's also Nishant and his group, TI, right? Okay. And then I'm the guy that gets to keep things going. As Nico pointed out, if we're powering down, a straightforward way initially to do it is to request the region, I want the whole thing, then power it down when it needs to power down, inside the game. There's also maybe powering it back up for board specific things. In the server cases, it's more of a problem because you have things like ECC, power the pseudo feed down, you've got ECC errors, they're not full memory, so you have to have something to do initially to clear the memory out. Or you just use the minesweeper, human minesweeper tactic, where you say, you know, I'm doing something dangerous right now. When you analyze every time you do a story, you say, oh, I got a mine, yeah, okay, fine, go. Anyway, but I don't know what kind of error protection we have on the mobile devices, if any. But none. So in that case, it's pretty straightforward. Just store it. All right. Powering back. Okay. Kernel code the cycle and the test plan we need, and which is the Java test.
But we should like this to be entirely implemented so that
Yes.
you just run it on a boundary force.
Yeah. So we want automated test plan. Okay.
Yes, for the first case, it's only generic code, so it doesn't need to be run on many boards.
Yeah.
Yep. The interesting one that requires a lot of boards, of course, really the fact that I ever have one.
You will also run it on universal songs and keyboards.
Yes, yeah, that's true.
Okay. Well, thanks for the coding. What we can do now is